I'll just jump straight to the answer here. If this slide is just too totally washed out looking, then I'll just redraw it if we need to do that. But the basic idea here of this matrix is we really only have two possible states. So that's represented here as our two rows. And then we have our individual observations. So you could think of this as the time step advancing along here. And let's just choose arbitrarily that this is time step t. And so what we're focused on is this state right here, f at time t. And one kind of intuitive way of making sense of all this is just to go back to what is the meaning of the forward-backward algorithm. It's basically the posterior probability of a specific state. So visually, you can think of that as the set of all possible paths that pass through that state, and effectively the total probability associated with all those paths that pass through that state divided by the total probability of all possible paths, right? So visually, you can just imagine that there's sort of this whole set of paths that all are forced to pass through this one point in the matrix. And the only parts that we care about, because we have a Markov property, which means we're not coupled to more distant states, is basically just the states that come directly into this from the previous time step and the states that we exit to in the next time step. So the forward-backward here can be visualized very simply as just basically the forward component that's going to be summing over all possible paths coming from time step t minus 1 entering to the fair state at time t. And then the backwards algorithm can just be thought of as the sum over all possible paths that are going to be exiting from the fair state at time t to the next time step t plus 1. I think, as I mentioned last time when I talked about the Viterbi matrix visualization, the direction of the arrows here, the way I'm drawing them, is kind of arbitrary, and you don't have to worry about the fact that I'm drawing them backwards here. However you want to draw them is fine. Just obviously they're conditional probabilities, so they do have they're directed edges. So then, I don't know, can you guys read this, or do you want me to rewrite it by hand?
It's okay. I can see it.
Well, let's see. Yeah, the front row says yes, and the rest of the class is silent. So I think I discovered that somehow or another the white balance for this had been set to completely blue. So I guess that meant that all the little portions of the videos where I wrote notes, I guess could be referred to as blue movies. But I've now corrected the white balance, so it should not be blue. All right, so we basically had this little zone, and we had edges going to time t, and then we had the exiting edges going to the subsequent states at time t plus 1. So our forward probability summation, the main thing, as I mentioned last time, for forward-backward is it's like you're taking the probability of all possible observations and you're cutting it right at t. And we just have to be careful when we cut that we don't include any probability component more than once. Right? That's, if you include a probability component more than once, it's like voting twice in an election. renders the result invalid. So in particular, when we're trying to cut basically this, and I'll explicitly write the 1 to n indexes on our observation sequence, we're going to cut that into two components basically right at t. So I'll write that theta t and then x1 to t. We just have to, yes. Yes, these are joint probabilities. Sorry, this word my comma would look too much like a 1. When we include this next factor, clearly we're going to have to include the x observations from t plus 1 on up to n. So I'll write that. And since we already included theta t once, we can't include it again. So we just condition on it. Okay? Does that make sense? So now this is the forward component, and this is the backwards component, simply because of the order in which we compute the forward component. It's always based upon the thing to the left of it, so we can compute them in order 1, 2, 3, 4, so on, forward. So my forward component, it always has this recursive definition, so basically I'll just write it in terms of itself, one step over to the left. So I'll just write this in terms of theta t minus 1. So I think you can see that that's just exactly the same thing, but just shift over to the left by one step. And we just have to think about what components we need to add on to this to get what we want to get. Well, over here we've got an xt, and over here we've got an xt minus 1, so we've got to get an xt. And over here we've got a theta t, and over here we've got a theta t minus 1, so we're going to have to get the probability of theta t as well. So basically, that's just the emission and the transition components, right? So I can just write, based upon my Markov property, this is only dependent upon theta t minus 1. So there's my transition component. And then my emission component, and the only thing I have to do now is I have to get rid of theta t minus 1. And I do that just by summing. So just to translate this again into the visual, so I'm specifically trying to get probability of theta t in the fair state for all the observations up to t. So I'm basically going to be getting this over. Well, I'll just write out the sum. There's only two components to it. Might as well just do that. So here I've got theta t minus 1 in, let's say, the fair state. I've got all my observations up to t minus 1. I've got the probability of fair given fair. And I've got the probability of my observation at time t given my fair state. And then we just have to do the same thing for the loaded state at time t minus 1. So t minus 1 equal loaded. and then all the observations up to t minus 1. Probability of fair given loaded, and then this part, the emission part, is just the same. So that's the forward component. The backward component we can write more or less in the same way. So we already wrote what the form is going to be. So that's going to be, I'll write this as the probability of the remaining observations, that's x, what did I say, t plus 1 to n given theta t in the fair state. I'll shift that up here, hopefully more visible. So I will write this again in the same form. I'll just shift it one over to the right. So P of x t plus 2 to n given theta t plus 1 to be, let's say, fair. So now I have to get from theta t fair to theta t plus 1 fair. So again, that's probability of fair given fair. And I also need to take into account observation t plus 1 that's present here, but not here, right? So again, I have an emission here for probability of x t plus 1 given fair. And then now I'm going to sum so now I have to have theta t plus 1 to be in the loaded state. I have the transition to loaded from fair, since I'm conditioning upon theta t to be fair. And now my observation at time t plus 1, but now from the loaded state. Okay? Does all that make sense? Any questions? Okay, so this, I think you'll agree, is the backward probability component that we were splitting this joint into two forward and backward parts, right? So just a general principle here, these are all recursive definitions, or, you know, we compute them recursively, I guess you could say. So I'm going to define this in terms of itself, but shift it over one step. So that basically means everywhere where you see a t, it turns into a t plus 1. Where you see a t plus 2, it turns into a t plus 2. Okay, so that's the backward component at the next position, one step to the right. And then in order to get this, I have to fill in basically the pieces that are missing. Question? Sure. Right. Right. So we're summing P of x t plus 2 to n given theta t plus 1, probability of theta t plus 1 given theta t probability of x t plus 1 given theta t plus 1, and I'm summing over here to get rid of theta t plus 1, because you'll see I don't have a theta t plus 1 here. So basically when you multiply these together, this is basically going to be the joint probability of x from t plus 1 to n and theta t plus 1 conditioned on theta t. And then I just sum over theta t plus 1 to eliminate it from the joint probability. So basically what we've just done here is we've kind of made the matchup of equation and picture, right? I think you'll agree the picture is simpler, but when we want to be fully explicit about exactly what is getting computed, all right, write out the equation. Other questions?
So is that just kind of like the next, like, the previous
Well, it's the backwards probability, but shifted over to the next at the next position. It's like if I were doing the forward-backward calculation at t plus 1 instead of at t. This would be my backwards component at time t plus 1. Other questions? Okay. Why don't you briefly click on the assess link.